Welcome to Maths with AJD. In this video, I'll be talking about non-homogeneous linear systems. In the previous video, right, I talked about homogeneous linear systems. And what makes the difference is the fact that we have a right-hand side, we have a system where AX is equal to 0, not instead of B that is non-zero. So for homogeneous, right, the case is different. Okay. So let's go for that now. So non-homogeneous linear ordinary differential equation systems are systems systems of ordinary differential equations that include a non-zero right-hand side, typically representing an external influence, or what we call a forcing term. Okay. So these systems take the form y prime of t equals a y of t plus f of t. So f of t now is the forcing term. So, for non-homogeneous, right, f of t will just be 0, basically. So here we say where y of t is the vector of unknown functions. Okay, then we say that A is a constant matrix. A is a constant matrix. And f of t is a non-homogeneous forcing term. Now, as for non-homogeneous linear systems, right, the solutions are not as straightforward as what we had for homogeneous. So we need to talk about this. And because of that, after this, I'll be making 2 or 3 other videos just to keep talking about non-homogeneous systems. So let's talk about the methods of solution. We've seen this already for uh, regular, maybe uh, not systems, right? Maybe first order, second order, like that. That is not system of equations. So methods of solution. So the first method of solution, we have come across it before, and it is called method of undetermined coefficients. Method of undetermined coefficients. Okay. So this method is used when f of t is of a specific form, such as polynomials, exponentials, sines, and cosines. So if the f of t is of any of these forms, then we can use method of undetermined coefficients, sines and cosines. If it is something like square root of something, maybe that would be difficult to do. So we have to think of other methods. Okay. So the solution, the solution is assumed to be a particular solution, okay, with undetermined coefficients. That's where it gets its name from. With undetermined coefficients, which are then solved by substituting into the ordinary differential equation. Okay, so to take an example, so for a system, y prime equals ay plus f of t, where f of t is equal to e raised power t 0, like this. So the particular solution, yp of t is assumed to be yp of t equals c1 e raised power t, and then c2 e raised power t, because if you keep differentiating e raised power t, you keep getting e raised power t, so it doesn't change form, right? So if it was sine, and then you can do c1 sine and then c1 sine plus c2 cos or something like that. Okay, so the coefficient now, so you can see c1 and c2 are undetermined, so, and that is the essence. So the coefficients c1 and c2 are then determined by substituting by substituting into the equation. Okay, into the equation. We've done this before, right? For second order, I think, second order problems. So it's the same thing, except that now we have a system of equations. Now let's talk about variation of parameters. Variation that was one, right? Method one. So the next method, which is method two, is method of variation of parameters. Method of variation of parameters. So here, this method works for a broader, so it works for a broader class of non-homogeneous terms f of t. You know, the other time, if you have exponent or a polynomial, sine and cosine, you can use undetermined coefficient. But here, what if you don't have any of those? That's where variation of parameters become very useful. Non-homogeneous terms f of t, especially when f of t is not easily matched to an assumed form, like in undetermined coefficients, okay? And then the solution involves finding the general solution corresponding general solution. Okay, so it involves finding the general solution to the corresponding homogeneous system and then applying a specific formula, for the particular solution. Okay. So a good example of that would be this. So for a system, y prime equals ay plus f of t, just the same like before, right? The homogeneous solution, the homogeneous solution is yc of t, and the particular solution, is given by yp of t equals yc of t, right? The yt of t would have got up there. Integral e raised power minus at f of t dt. So that's how this goes. So yp of t equals yc of t integral e raised power minus at f of t dt. That's how we have this. So that's another method we can use for solving non-homogeneous linear systems, undetermined coefficient, variation of parameters. Then, in this case, I want to introduce a concept which is not a new idea altogether, for sure. But I mean, if I'm going to treat this as a separate playlist later because it's really important. So it helps to solve differential equations, even not only systems, right? So it's so powerful. So, and it is called the Laplace transform. So I think after system of equations, I'm going to treat transform as a standalone playlist, which I'm going to add to the playlist for differential equations. Okay. So look out for that by applying the Laplace transform, to both sides, of the system. So of the system, any system, non-homogeneous system you are given. So you convert the differential equations. You convert the differential equations into algebraic equations. So you see, Laplace transform converts differential equation into algebraic equations. And algebraic equations are more amenable to solution than differential equations, right? Like at least relatively. So into algebraic equations, which are easier to solve for sure. Just like I said, easier to solve. Okay. So then after solving for the Laplace transformed variables, the inverse transform, so you now use Laplace transform again to take it back. The inverse transform is used to obtain the solution in the original time domain. Okay. So a good example is if y prime is ay plus f of t with, so now the beauty of this one is that it also incorporates initial conditions. So you get particular solutions at the end of the day. So if y prime is equal to ay plus f of t with initial conditions, y of 0 equals y naught, then take the Laplace transform, to get s y sy of s minus y naught equals a y of s plus f of s. Okay, so Laplace transform makes it all into algebraic like this. So, I mean, that's how that works. Okay. So in conclusion, right, we've seen different things so far. In conclusion, so you've seen all these different methods. So these methods allow you to solve non-homogeneous linear ODE systems, ordinary differential equation systems, in various scenarios. So, I mean, when you see the problem, you have to know which method will be best for it. With the choice of method, okay, depending on the specific, form of the forcing term, f of t. So with this, we come to the end of this introductory video to the non-homogeneous linear systems. So in the next 3 videos, I'll be looking at these methods, except Laplace, which I'm going to take later as a standalone playlist to be added to the differential equations playlist. Okay, so watch out for this. So if you have not subscribed to this channel, you may be missing out on that. So please go ahead, subscribe right away. If you have subscribed, thank you so much for that. And everybody, don't forget to hit the notification bell so you can always get alerted each time a new video is released. Then of course, let me know in the comments how helpful these videos are for you, and if you need me to teach a topic or solve a problem, I may be able to find time to do all of that. Then don't forget to like and share so that more people can have access to this great content. So like, come your way again, keep doing maths right. Watch out for an elaborate explanation of the method of undetermined coefficients for this kind of non-homogeneous linear systems. Bye.